Now, in this session, we will see an RL transient circuit with a switch S toggling between position 1 and position 2, wherein a 100-volt DC supply is connected to position 1 and a direct line is connected at position 2. At time t equal to 0, this switching to position 2 takes place. Also, it is said that in the problem, the position 1 is connected for a very long time. So, it means that till steady state value is reached, the switch was in position 1. Now, at time t is equal to 0, for the given condition, it is said that the switch is connected to position number 2. Now accordingly, we have to see that whether any initial current flows through the circuit at the instant when the time interval is before the switching of position number 2 takes place, that is at the instant t is equal to 0 minus, which means that the previous instant whether any network current is being flowing through the circuit. Now it is said that when the switch is connected at position number 1, then a voltage source is connected, and due to which the current will be flowing through the circuit. So the voltage connected is 100 volt. So at that instant, what is the current flowing through the circuit? So we know as per the inductor, it cannot take sudden change of current. So therefore, for a very long time, if the switch was connected at position number 1, it means that the current flowing through the circuit will be in accordance with the Ohm's law, I is equal to V by R. So at that time instant, your I of t will be equal to 100 divided by R. Here two resistors are given, one is 20 ohms and the other one is 30 ohms. So therefore we will be having sum of 20 plus 30, that is 50 ohms. So 100 by 50, we will be getting it as 2 amps. So this 2 amps is the current flowing through the circuit when it is connected at position 1 for a very long time. The current starts to increase at the instant of switching, then gets stabilized as time proceeds. So this is what had happened at position number 1. Now when the switch is connected to position number 2, at that instant the inductor will not take any sudden change of current. So what happens is the previous current tends to flow at the instant of switching, that is at t is equal to 0 plus, at that instant of switching, whatever was the previous current, it will try to flow into the circuit. So this we will call it as initial current. So therefore at t is equal to 0 plus, the current which is flowing through the circuit when the switch is brought at position 2 is your previous current, which is 2 amps. So that I naught will be taken as 2 amps, that is the initial current which is flowing through the circuit at position number 2. RL and direct short is connected from position 2 to ground, and the respective resistor and inductor values are connected in series. Now at this position, the current will not be flowing in the clockwise direction, whereas it will be flowing from the inductor around the circuit, that is in the anti-clockwise direction. Apply KVL to the above circuit, we will be getting sum of source is equal to sum of voltage drops. Now accordingly, the circuit has no source, so therefore it is equal to 0, which is equal to sum of drops. One is resistive drop, the other one is inductive drop. So therefore we will be having 30 I of t plus 0.2 d by dt of I of t. So this is the expression we get governing this circuit by applying KVL. Take Laplace transform of the equation. So therefore it will be 0 equal to 30 I of s plus the differential equation Laplace transform will be 0.2 the whole bracket of s into I of s minus I of 0 close brackets. So this is the expression we get after taking Laplace transform. Here I of 0 is the current which is flowing initially in the circuit before the instant the switching takes place to position number 2. So before that instant it was originally connected to position 1 for a very long time period, for which we had calculated the current to be equal to 2 amps. So that value is the initial current which will be flowing through the circuit after the switching takes place, that is I of 0 plus. So therefore we will take I of 0 is equal to I of 0 plus is equal to 2 amps. Now we will be substituting 2 amps in place of I naught. So therefore we will be getting 30 I of s plus 0.2 open brackets s into I of s minus 2 close brackets equal to 0. We will simplify it further in order to find out the current in S domain. So therefore 30 I of s plus 0.2 into s into I of s minus 0.2 into 2 equal to 0. So therefore further simplification, I of s is taken out from first two terms, that is 30 plus 0.2 s minus 0.4, which is taken to the right side, it becomes positive 0.4. So which is the result of 0.2 into 2. Now I of s is equal to 0.4 divided by 30 plus 0.2 s. Now take the coefficient of s outside so that we will be getting the form as s plus a, where a is the constant. So therefore in order to get that condition, let us take 0.2 outside. So hence 0.4 divided by 0.2 is taken outside. So therefore 0.2 into 30 by 0.2 plus s. Now 0.4 divided by 0.2 the whole divided by 30 by 0.2 will give you 150. So hence we can write it as the s plus 150. So this is the expression for current in S domain. Now we have to take inverse Laplace transform of this expression, and 0.4 by 0.2 we will be getting it as 2. Hence I of s is equal to 2 divided by s plus 150. Now for this, if we take inverse Laplace transform on both sides, we will be getting the current expression in time domain. Therefore we get I of t equal to 2 is a constant which will be written as such, and 1 by s plus 150 has to be taken inverse Laplace transform. The general rule for applying Laplace transform inverse for 1 by s plus a is equal to e power of minus at, where a is the constant value. So based upon that we will be writing the expression for current, which is taken for our case as 2 into e power of minus 150 t. Now this expression shows the decaying transient of the current. Now let us see the graph of this current expression. How do we say this as a decaying transient? Let us draw the graph with the x-axis in time domain and y-axis as current. Now the expression starts with 2 into e power of minus 150 t. So therefore 2 is fixed at the top. So from there it starts decreasing. Let us see how it starts decreasing from the expression. Now say for instance time is equal to 0. So, therefore, upon substituting t equal to 0, we get the current expression I of t will be equal to 2 into e power of 0 is equal to 1. So, therefore, 2 into 1, 2 amps. So, it starts from 2 amps at 0 instant of time. So, therefore, t tends to infinity as time proceeds. Your current I of t will be equal to 2 into e power of infinity, which will be 0. So, therefore, I of t will be 0 for infinite time. Hence, we get a decaying current transient. Thank you.